I would like to introduce Thomas King, who will be presenting PeeringLAN 2.0, Introduction to EVPN at DE-CIX. Thomas is, he is the CTO at DE-CIX and is coming to us today from Frankfurt, Germany. This is Thomas's first time presenting at NANOG, and it's a pleasure to have him with us today. Let's give him a big round to start with and an even bigger round when he's done. Welcome, Thomas.
So I believe it's not my first time presenting at NANOG, but still, again, it's great being back on stage. So welcome also from my side. I'm Thomas, I'm the CTO at DE-CIX, and I want to talk about PeeringLAN 2.0 and the introduction of EVPN at DE-CIX. And this is mainly a report of what we have done in the last couple of months. And if you are a customer of us, you probably have seen a lot of announcement emails for maintenance windows. And what I want to present here is give you a bigger picture of why we did this, what is in for you as a customer, and how well did it work. Let me start. So, if you run large PeeringLANs as we do, there are some challenges, and I want to highlight two of them and how we came up with a solution for that. So if you look at DE-CIX Frankfurt, it's our largest PeeringLAN which we run with about 1,000 ASNs and roughly 1,300 peering sessions alone via the route servers for IPv4 and for IPv6. And there are, of course, a lot of bilateral peering sessions which we don't see how many there are, but there are also a lot of them, right? And at peak times, you guys push 14.4 terabits of traffic over this PeeringLAN. And if you look at our second largest PeeringLAN, it's DE-CIX New York. We have about 260 ASNs connected and roughly 300 peering sessions via the route servers on IPv4 and IPv6. And we just hit 1 to 3 terabits of traffic last night. So thanks, Valerie, for updating the slides on last very ad hoc, so that's great. And why I'm highlighting this is because if you see all these routers connected to the PeeringLAN and using IPv4 and IPv6, you usually have a lot of ARP and neighbor discovery traffic. We call that also boom traffic, so it's broadcast, unicast, and multicast traffic, and you see a lot of this. And here, this picture is this graph is from DE-CIX Frankfurt. So for ARP and neighbor discovery traffic, we had about 2 megabits of this. And this, for some of the routers, is just too much because the ARP and neighbor discovery still goes to the CPU and is handled in software, right? Juniper devices, for instance, if you take them out of the box and just plug them into the PeeringLAN, they don't work. So, of course, we helped our customers updating the default policies on the ARP and neighbor discovery so that they can handle this massive amount of traffic. But I am, as a CTO, I'm not happy when my customers need to do something additionally to bring the gear up and running and make sure it works smoothly in such a PeeringLAN, right? So that was one issue which we faced. Another one is that ProxyARP and neighbor discovery at customer routers is an attack vector to the whole PeeringLAN. And I just learned a nice use case for ProxyARP from Mike, the earlier session, right? He was also talking about ProxyARP. But in a PeeringLAN, it can have a catastrophic impact. So how does it work? So you have a PeeringLAN. This is our yellow cloud here. You have different routers connected to it. In this example, we have router 1 and 2 and a few others. And usually traffic just flows between the routers, right? This is how it should be. But what can happen is if one of these routers, in this example router 2, switches on ProxyARP, then this router is replying to the ARP and neighbor discovery requests coming in by his own MAC address. And so what, if the timing is right, so what will happen is all the traffic goes to this particular router and overwhelms this router. We at DE-CIX, in the past, we spent a lot of time, and also we had tools to detect if something like this is happening. But we could only react to such an incident because technically we couldn't prevent it. happening. So when such a situation happens, and then it's usually catastrophic to the peering LAN, because then the traffic is not flowing smoothly anymore, and that is something we try to avoid to the maximum, right? So we had tools in place monitoring this and shutting off routers which switched on ProxyARP and neighbor discovery automatically, but still the impact usually took us 10 minutes, 50 minutes, 20 minutes, depending on how quickly we could detect that, and that is not a good thing. And we realized things like this happens once or twice a year usually, sometimes a bit more than that, depends how carefully people configure their routers, right? So this happens, and it is something we wanted to get rid of. So what we did is we were working on what we call PeeringLAN 2.0, and we were working together with Nokia and a few others to standardize how that works, and that is coined out in RFC 9161, where we basically enhance EVPN for the PeeringLAN use case. And let me walk you through how that works. So here we have the PeeringLAN again, the yellow cloud, and then we have two routers connected to that. You know, as an operator of a PeeringLAN, you give out to the peers the IP addresses they need to use to be part of the PeeringLAN. And at DE-CIX, at least, we take port security very seriously. So we want to know what is the MAC address of the router that is connected to the PeeringLAN. What does it mean? We already have the bindings between the IP address and the MAC address, and we can then feed that into the ARP and neighbor discovery proxy agent, which comes as part of EVPN. And actually, this is what we do. We feed that into the ARP and neighbor discovery proxy agent, make sure that this agent snoops the ARP and neighbor discovery requests that come in from customer routers, and make sure that they don't flood the PeeringLAN. And then, as we have the static binding already, we can directly send back the response. And if you do that, then even if router 2 is switching on ProxyARP and neighbor discovery, then the attack vector disappeared, right? Because there is no flooding of ARP and neighbor discovery requests anymore. So yeah, the router 2 doesn't see the requests anymore, so it can't falsely reply to these requests. And at the same time, routers don't see the ARP requests from others anymore, so the load on the different routers is going down also. So this sounds technically wise like a perfect solution for the issues which we had, right? So the question is how to roll it out, because this is, you know, and if you would build a new network, you can easily deploy that. But if you have a large network, as we have, with nowadays 40 locations globally, and roughly 3,000 customers connected, you need to be very careful how to migrate to such a solution. So, and in the next couple of slides, I want to show you what we did to make it happen. So we were looking into different migration scenarios. First, we were thinking, okay, let's do it router by router. That is, you know, small steps, pretty simple. We can do that. But you know, if you think about that, we run about 70 routers globally. You need to make sure that you do it in the right order. And a PeeringLAN consists of different routers which we run to build the PeeringLAN. So we realized, wow, complexity is actually quite high. And downtime for customers will be, you know, in hours or probably even days if we do it, depending on how we do it. So it's probably not the right thing to do. Then we were thinking, okay, let's do it location by location, because a PeeringLAN, let's say in New York, consists of, I don't know, 15 routers based in New York. Could we just take them and migrate them over to the EVPN solution? So we're looking into that, realizing it's not perfect, but probably doing it service by service, meaning PeeringLAN by PeeringLAN. That could do the trick, because we have also customers coming in remotely, right? So a PeeringLAN, for instance, in New York, also is accessible out from Frankfurt, because we have a lot of peers being physically in Frankfurt, but still want to be part of the PeeringLAN in New York. So we were looking into that, and the beauty of it is because we wanted to minimize the downtime for customers to the maximum, that this showed us that would be the right thing to do. So we followed up on this, even knowing that the lifting for us might be a bit more complex, but yeah. So to make customers happy, that is the right thing to do. So we followed up on this. And if you want to change the configuration of a network so heavily, we were pretty sure we need to test it very heavily, because there's only one shot where we can really do the migration. We can't. Of course, we prepared also for rollbacks, but we didn't want to do that, right? We wanted to roll it out, and it needs to be perfect for our customers. So what we did is we were building in our lab parts of the networks. We were taking the building blocks, the critical building blocks, which we have. So mainly Frankfurt, New York, because these are the two largest PeeringLANs which we have, and we have cores there because we need to have a distribution of the traffic. So we are building parts of this in our lab, and also we are bringing in Dallas, because Dallas is strongly connected to New York, for instance. So we are building part of the network in our lab to do tests. But hardware tests is fine. But what we learned is software is even better, because you can change it more quickly. So we emulated a lot of the network in software, so that we could run tests repeatedly and detect if, for instance, something is wrong with our configuration, because we were taking the configuration, the live configuration of the network, which we were running at that point in time, and we're loading it into software to see if there's some anomalies. And funnily, we found, of course, manual configuration, which we have done. We have a very strong automation tool chain, but here and there, our network engineers, to help customers with an issue, we are doing some manual tweaking. And we also found one borrowed line card. We totally forgot about it. At one point in time, we are using Nokia, right? And we ordered one particular line card, but they couldn't deliver that one, so they gave us a different one. But that different one couldn't run EVPN, because it was not as powerful as the ones we usually use. So, but we totally forgot about it. And when we did this testing, we realized this line card isn't capable of running this feature set. So we needed to clean that all up and made sure that this runs smoothly. And then when you introduce a new configuration, right, so you have new configuration generators, you want to be 100% sure that the service that comes out of these new configuration generators for customers is exactly the same thing what you had previously in terms of what they can expect from you. So we had a lot of test cases for our configuration generators, and that in the end, I think, did the trick to make sure that this migration went smoothly. If you look at the tool chain which we have for automation at DE-CIX, it's actually a pretty complex thing, because we have nowadays APIs for customers to directly connect to us, self-service portal, our customer service is using also a tool Artemis. It's different from the last presentation, but this is a web app where they can help customers troubleshoot and provision services. So we have different data sources, Netbox, of course, some own homegrown databases which we are using to, customer data, which were needed to then generate the configuration. So as the DE-CIX automation toolchain is, of course, a lot of software, we could do also a lot of testing here. And then finally, we were ready. So we spent roughly 6, 7, 8 months on preparing everything, doing all the testing, getting remove the old borrowed line card and things like that. And then we started the migration on 1st of November with DE-CIX Phoenix first. Why DE-CIX Phoenix? It's a pretty simple setup from our perspective, so it's not a lot of routers involved. Not so many customers connected, so sorry for the customers connected in Phoenix. And don't get me wrong, we wanted to make customers happy, but you need to start somewhere. And if you are, if you do such a big migration, you take the smallest, you accept the smallest hit, right? But everything went very well. So we did the migration. It was done in a couple of minutes. I was very happy with the team, how well they prepared it and how well it worked. And then we waited for 1 week to see if, is it really stable over time? All our monitoring tools and things like that, do they work as expected? And yes, that was great. Then we directly moved on to DE-CIX Frankfurt, which is our largest PeeringLAN, and a lot more complex than Phoenix. That worked also like a charm. So it was. I was very, very happy with that. So then we moved on a weekly schedule, migrating one service after another. The 29th of November, we also migrated all the remaining PeeringLANs in the US. And then 6 weeks into the migrations, we then finalized migrating all the other interconnection services like direct cloud and closed user groups and things like that. So it took us 6 weeks, and it just went flawlessly, which was great. And this is how the team looks like, because I'm just the guy giving the presentation, right? So all the heavy lifting is was done by these guys. And I took that picture at 4 a.m., roughly 4 a.m. in the morning when we migrated DE-CIX Frankfurt. So you see, the people are not smiling so heavily because I'm quite tired, I guess. Yeah. So let's look on the results. Did the results show up as expected? Yes, they did. Here you see the same graphs as before, right? You see the ARP and ever discovery traffic in our traditional PeeringLAN setup. Then we had a migration for about 20 minutes or something. And then when the whole thing came back up online, you see that the PeeringLAN 2.0 solution with the EVPN really reduced the ARP and ever discovery traffic a lot. So we were coming from roughly 2 megabits to a little bit more than 500 megs. Yeah, so that looks good and on the total overview. But now if you look, take the customer view and look at one port in the traditional setup, a customer was seeing about 800 ARP requests a second. And about 1,400 neighbor discovery requests a second before we did the migration. After it was only 8 ARP requests and 53 or roughly 50 IPv6 neighbor discovery requests. So it reduced the amount of requests tremendously, as expected, right? So that worked, and we got a lot of great feedback. If you follow us on Twitter and or LinkedIn or something, people were, the CPU load of my router dropped by 25% and things like that. So people were very happy about this change. But I want to also share the not so nice things. Because if you do such a big migration, there are some hiccups and bugs and issues which you sometimes face. So what we learned, because we were also changing some MPLS fundamentals, I didn't report about that, but what we hit was a bug with Nokia implementation of the LDP entropy labels, because lag members, the traffic in lag members wasn't well balanced after we implemented that change. So we implemented during the same maintenance window a workaround to fix that. But the investigation is still ongoing with Nokia to understand what's exactly happening here and why is the entropy label stuff not working as expected. And we hit a bug with the IPv6 neighbor discovery agent, which sometimes replies with wrong source IP addresses. So this, especially with Juniper hardware, can cause issues. So we disabled it for the moment. We need to replace the router OS with a bug-fixed version. It's already out there, but we need to, do maintenance on the routers and upgrade the OSs. We expect to do that in Q2, and hopefully then everything is back to normal. So yeah, this brings me pretty much to the end of this presentation. I hope I showed you what PeeringLAN 2.0 is bringing to you, how it helps you running your networks more easily, more stable, and I'm open to questions. So no questions. Thank you very much.
you.